Hi, I'd like to talk about graphing polynomial functions. And before I jump in, I want to let you know that I'm going to assume that you've already watched the writing equations of polynomial functions video that I did. In the first half of that video, I discussed the way that some polynomial functions look, and we talked about the zeros of polynomial functions. In this video, I want to start by discussing the way a polynomial function looks as it relates to the degree of that polynomial function. So let's go. Let's start with polynomial functions that are degree 2. That means they're second degree or quadratic functions. And you are probably already familiar with them. That means they're functions that look like this. F of x equals ax squared plus bx plus c. I hope you know already that this would have a graph that looks like a parabola. And depending on whether a is positive or negative, the parabola could open up or open down. If the parabola is, if a is positive, we have a parabola that opens up. And if a is negative, we have a parabola that opens down. We know that parabolas are smooth, continuous curves, as are all our polynomial functions. And I am going to point out that right here, the graph turns from decreasing to increasing. And here, the graph turns from increasing to decreasing. So with this second degree polynomial, there is one turning point. That's very important, so let's write that down. We'll say that there is one turning point, or one maximum or minimum point on the curve. Let's continue. I'd like to turn to third degree polynomials. So that means the term of highest degree in the polynomial function is degree 3. So let's look at a few. Here are the graphs of a variety of third degree polynomials. Notice the equations are all a little bit different. This polynomial function right here is missing the linear term. This one's missing the quadratic term. And by missing, I mean the coefficient of that term would be 0. The details of the graphs are a bit different. Notice the fourth one, this one right here, the numbers are so large I had to change the scale. This number appears at 200 rather than a 20, as you see on the other graphs. But in general, they have the same sort of look. So we can say that f of x equals ax cubed plus some other stuff kind of looks like this if a is a positive number. Notice the only one where the leading coefficient was negative was the last one. Right here, the leading coefficient was -2, and notice it looks like this. And this is true in general. If a is negative, it's going to start up here and go down this direction. Now, sometimes I think of these graphs as if they're made of string, and notice in the third graph, it looks like somebody just took the string and pulled it out a bit, so we lost the turning points, those maximum and minimum values. But notice on all the others, here was one maximum and here was a minimum, 2 turning points. 1, 2 turning points. This one we lost them, so we had 0 turning points. 1, 2 turning points. And in this one, 1, 2 turning points. So let's write that down. Third degree polynomial functions, when you look at their graph, have at most 2 turning points. Remember, with our second degree polynomial functions, we had 1 turning point. With degree 3, we're looking at most 2 turning points. Let's move on and talk about fourth degree polynomial functions. So here are some examples of some fourth degree polynomial functions. Notice the similarities. Of course, I had to change the scales, but in the end, we can see they look very similar. Notice it starts up here and goes down and up and down and back up. This one does the same thing. And this one, let's go down here to the lower right, is the same kind of thing, but it goes up and back down, and it's because of this leading coefficient being negative that it's sort of upside down. But do you see how this kind of looks like a W? This looks like a W. This is an upside down W. And as with the third degree polynomials, I think of these as being made of string almost. Somebody pulled this one out a little bit and we got rid of the maximum and minimum values. And in fact, this is looks like our power function that's been just shifted over 1 unit. And that is in fact what it is. It's y equals x to the fourth that's been shifted to the right 1 unit. And I just multiplied out the polynomial function. Notice over here in this function, it looks like somebody took the string and pulled it out a little bit. So we only have this one minimum value. Let's look at our turning points. 1, 2, 3. 1, 2, 3. Just one. Just one. And 1, 2, 3. For a fourth degree polynomial, we have at most 3 turning points. Do you remember? For degree 2, we had 1 turning point. Degree 3, we had at most 2 turning points. Degree 4, we have at most 3 turning points. And that will be a pattern you'll see no matter the degree of the polynomial. If the degree of the polynomial is n, you can have at most n minus 1 turning points. But let's talk about what our function looks like when we graph it. Let's draw it down here as we did with our third degree polynomial. If f of x equals ax to the fourth plus some other terms, I just wrote the leading term. If the leading term has a coefficient that is positive, generically speaking, our fourth degree polynomial is going to look something like that. We do know that it could be pulled out a little bit and take on this kind of a look, but generically speaking, we expect it to look like this. And if a is negative, in other words, the leading coefficient is negative, we expect it to look something like this. So we're going to look at our fifth degree polynomial functions. Remember when we were looking at the fourth degrees, I said it just a minute ago, that if you have degree n, the number of turning points will it be at most n minus 1. So if that's the case, we expect to have at most 4 turning points. That means at most 4 maximums or minimums. Let's look at some graphs and see that that seems to be true. Here are some examples of the graphs of fifth degree polynomials. Look at the first one. We have 1, 2, 3, 4 turning points. On the next one, notice we have 1, 2 turning points. It looks kind of like a degree 3 polynomial, but in fact, look at the equation. It is a fifth degree polynomial equation, and that's its graph. And look at this last one, and notice the scale that I had to use. Up here, it's at 10,000 and negative 10,000, and look at these numbers. I had to change the scale, but the essence of the graph still looks like the first one, except our leading coefficient is negative. So instead of starting at the bottom over here and moving up to the top, it starts way up here and it comes down over this direction. right? That negative coefficient is what makes the difference. But notice there are 1, 2, 3, 4 turning points. Again, as we would expect for a fifth degree polynomial. So if we have f of x equals a times x to the fifth plus some other terms, we expect the polynomial graph to look something like this, generically speaking. It can degenerate and look more like this second graph right here, look like a third degree, sort of like somebody took the string and pulled it out and we lost one of the maximum and minimum values, but it's still a fifth degree polynomial. And this is what we expect if a is greater than 0. If we have a fifth degree polynomial, and the leading coefficient is negative, in other words, a is negative, then we expect it to look more like the last one, generically speaking, something like this. So let's look at a summary of what the graphs of polynomial functions look like. I have them listed here. And notice it is the leading term that is really critical when you're determining what the graph looks like. The leading term that controls the degree of your polynomial. Remember, the leading term is the term of highest degree. So when we have a second degree polynomial, we expect it to look like this when we graph it. A third degree polynomial would look like this, 2 turning points at most. We know it can degenerate and look like its power function, that is this. Similarly, our fourth degree can have 3 turning points, and our fifth degree can have 4 turning points. Notice when the leading coefficient is positive, this is the way our polynomial graphs look. And if a is negative, then they're looking like this. What you can count on for sure is that the polynomial function in the end will take on the look of the power function of its leading term. So with this fifth degree polynomial, what I know is in the end, and we do call that the end behavior, that the graph will be going up this way and down this way. We don't necessarily know what the details will be in the middle, but we are guaranteed that's what it will look like in the end if a is positive. And if a is negative, we're guaranteed it will look like this, just like its related power function would look. And by related power function, I'm talking about these down here. If we ignore the part in the middle and we just look at where the graph goes when x's get big, when you move to the right, what happens? Where does the graph go? And when x's get small, if you move to the left, where does the graph go? So for our fourth degree polynomials, if a is positive, we know for sure that the graph will be going up both when you move to the left and you move to the right. And if a is negative, we know that it will be heading down if you move to the right or to the left. Again, we don't know about the details in the middle unless we do more work. So we're going to put all of this together and practice some problems. So let's start with this one. Sketch the graph. We're going to use the degree and the leading coefficient from the polynomial to help us figure out what the graph should look like. And we're going to use the zeros and the multiplicity of those zeros to help us figure out the details. So here we go. We have y equals x plus 1 times x minus 2 times x plus 3. Notice if we were to multiply this out, we would have y equals x times x times x, that is 1x cubed, plus some other terms. And I don't really care what those other terms are. I wanted to know that that was an x cubed because I'm thinking about what a third degree polynomial looks like. So in my head, I'm thinking, okay, generically speaking, looks like this. Now let's figure out the details. The zeros are the numbers that make the function equal to 0. We set each factor equal to 0, so we would have -1. Notice its multiplicity is 1 because the exponent right here is 1, as the exponent is on each of our factors. So multiplicity 1. Then we have 2 with multiplicity 1 and -3 with multiplicity 1. Let's get a decent sketch for this. So I have -1, 2, and a -3. And we know what the graph looks like. It's end behavior at least. We know that to the right, as the x get bigger, it's going up this way. And to the left, it's heading down this way. And the intercepts and the multiplicity are going to help us figure out the details. So if the graph comes from above, I'm going to start over here. When I get to 2, I look at the multiplicity and I see it's odd. That means it crosses. I don't know how low it goes. I don't really care with my rough sketch. I'm going to turn around and I come back up, and at -1, let's see, multiplicity is odd. It crosses again. And then it goes up. I don't know how high. I'm going to turn around, and at -3, I see I have multiplicity 1, and it crosses again. And I have my sketch. I don't really need those arrows that I put there for the end behavior. Let me erase those. That just helped me figure out how it looked. I would also like to label this y-intercept right here. Since I don't have any scale on the y-axis at all, let's see, if x is 0, y would equal 0 plus 1 times 0 minus 2 times 0 plus 3. That is 1 times -2 times 3. That's -6. And it's done. I have my rough sketch complete. Notice I have a smooth, continuous curve. I didn't have to pick up my pencil anywhere to draw it. I should be able to draw it without picking up my pencil because it's continuous. It's also smooth. There aren't any sharp turns. Sometimes I see graphs that look like this. If you find that you have a sharp turn, it is not the graph of a polynomial function. So let me erase that. One more thing that is important to know. Unlike quadratic functions, where the maximum is exactly halfway between the x-intercepts, we have no guarantee that the maximum value would be attained halfway between the intercepts. So for example, on this graph, -3 and -1, it kind of looks like on my graph that the maximum is at -2, but we in fact have no guarantee that that is the case. How would you find that point? Well, you'll take calculus and learn how to do it. That is beyond the scope of this class. You could plot some points and figure out about where it is, but that wouldn't tell us exactly where it is. So we're just looking for a rough sketch. So let's see how it looks when the computer does it. There's the graph. Notice it looks a little bit prettier when they did it, but the essence of the graph we have. Let's go on. So here's our next one. Sketch the graph of f of x equals x squared times x minus 3 times x plus 4. Let's start with the degree. We have an x squared times x times x. So if we were to multiply this out, we would have f of x equals 1x to the 4th plus some other terms, but it is that leading term that we care about. So a 4th degree polynomial with a leading coefficient that's positive, I expect the graph to look something like this. Kind of has that look of a W. And those don't go straight up, but they are relatively steep. So let's start with our zeros, or continue with our zeros. Our zeros are from this x squared. We see we would have a 0, and its multiplicity is 2. Notice that exponent. Then we would have a 0 of 3 from our next factor, and notice its multiplicity is 1. And then our last 0 is -4 with a multiplicity of 1. So let's draw our graph. We'll put our zeros on the graph. We have 0, 3, and -4. And our end behavior comes from this. We know it will be above, coming from up here to the left. That means over here. The graph is up here. And then over to the right, it's going to be up there as well. So sometimes I just put a little mark there going, okay, my graph is going to be here and here. And then I use the zeros and the multiplicity of those zeros to help me come up with the graph. So if I start up here, I'm going to come down, and at -4, I see the multiplicity is 1. That means it crosses. How low does it go? Don't know. I'll just turn around somewhere. And then our graph comes up, and at 0, the multiplicity is 2. Remember, that means it is just tangent. It just touches and goes away. Goes back the way it came, so back down. And then I'm coming down, and then I turn around at some point, and at 3, it crosses again, and we have the graph. I always label both the x-intercepts and the y-intercept. The y-intercept is the origin, so there's nothing else to be done. And we have it finished. Here's our next example. We're going to graph g of x equals 1/2 times x plus 1 to the third times x minus 4 times x plus 3. If we were to multiply that out, what would the leading coefficient or the leading term be? It would be 1/2 times x to the third times x. So we would have 1/2 x to the 5th power plus some other stuff. So generically speaking, our graph could look something like this. But we don't know the details. What we do have a guarantee about is that we know in the end behavior is going to be just like this. It's going to be going up this direction and down that direction. That's guaranteed. We don't know so much about the details in the middle. So let's get going. Let's start with our zeros. Remember, a constant does not generate a 0, but we have -1 as a 0 with multiplicity 3. 4 is a 0 with multiplicity 1. And a -3 is a 0 with multiplicity 1. So let's see what we come up with. Our zeros will be labeled down here at -1 and at 4 and at -3. I know my graph. We saw the end behavior. It's going to be up here. And let's see, down here. So here we go. We're just going to use the multiplicity to figure out what it looks like. If we start down here, we get up to to the -3. We see that the multiplicity is odd, so it crosses. Goes up how high, we don't know. At -1, the multiplicity is odd, so it crosses. It goes down a ways. How low? Don't know. And then we come back up, and it will cross 4 because the multiplicity is odd again. And it's complete, almost. There are a couple of details I want to talk about. One, I want to label this y-intercept. So we find our y-intercept by making x equal to 0. So we have g of 0 equals 1/2 times 0 plus 1 cubed times 0 minus 4 times 0 plus 3. So we have 1/2 times 1 times -4 times 3, and that is -6. Now I want you to look at the graph as the computer comes up with the result. Here's how it looks when the computer generates the graph. Now, at first you might think that doesn't look anything like our graph, but notice our intercepts are right. -3, -1, and 4. -3, -1, and 4. Our y-intercept is correct. I didn't have it going nearly as low, though. And you could generate that by plotting points if it was necessary. But at a rough sketch, and a very rough, we have the essence of it. We know when the graph goes up, when it goes down, when it goes back up again. But there is one other detail that I want to point out to you. Notice right here at -1, the graph flattens out. That's because we have multiplicity 3. So we should have known, or I could have told you, but I wanted to surprise you, that the graph will come down and flatten out as it goes through the 0. In fact, the graphs take on the look of their power functions at their x-intercepts. And I'm going to show you what I mean about that on the next example. But let's fix this one first just a little bit. So right in here, we now know it doesn't do this. We know that we should flatten it out a little bit. Comes up, and when we see that multiplicity 3, we know it flattens out there, and then it will come down and back up. So I fixed that a little bit. Here's my -1. It doesn't look nearly as nice as the graph the computer did, but there's my picture after I erase a little bit. I'm just going to erase a little bit more so that it looks a little bit better. But you want to make sure the general shape is correct, the intercepts are correct, and the graph goes through the zeros the way that they should. So let me tell you what I mean about the graph looking like its power function at the zeros. We'll look at the next problem. Let's look at the graph of y equals x plus 1 cubed times x minus 2 squared times x plus 4 to the first power. I already have the zeros listed. I have the multiplicity listed. So let's compare that to the graph. Here it is. Now let's look at the 0, -1 right here. Its multiplicity is 3. Remember that a power function that is third degree is y equals x cubed. And remember that y equals x cubed is something that looks like this. It goes through -1 just like our power function goes through the origin. It flattens out right here. That's the way it's going to go through the 0. So it flattens out there. Let's go on to the next 0. 2 with multiplicity 2. Well, remember a polynomial with degree 2, y equals x squared, is a parabola. So we expect the graph to look kind of like a parabola, not exactly, as it approaches the intercept right here. So look at this right here. If you get really close, it kind of looks like a parabola. In the same way, this kind of looked like y equals x cubed. And right over here at -4, we're talking about something that is first degree. We know a first degree polynomial is just a line. And notice, if you look at it closely, it is not a line, but it kind of looks like a line. So the multiplicity does tell us something about how the graph goes through the 0 or touches the 0. And by the way, right here, we have right here at 2, the multiplicity was 2. So it kind of looked like a parabola. If the multiplicity had been a bigger number, like 4 or 6 or 8, it would have flattened out more as those power functions do. So we're going to keep that in mind when we graph our next one. So we're going to sketch the graph of f of x equals 5 minus x times x plus 2 cubed. Let's look at our leading term. It will come from negative x times x cubed. So if we were to multiply this polynomial out, we would have f of x equals negative x to the 4th plus some other terms. So let's see, an x to the 4th graph with a negative coefficient means our graph would look something like this. So let's see how our zeros will affect our graph. We know we have 5 as a 0 from that first factor with multiplicity 1. And negative 2 comes from our second factor with multiplicity 3. So let me draw my grid. I'm expecting the end behavior to look like this. This is the important part. Down here, down here. So my graph will be down here somewhere and down here. I just don't know the details in the middle. So let's put on the zeros and figure out what this graph looks like. So negative 2, negative 1, negative 2 right here, and 5. 1, 2, 3, 4, 5 right here. So I'm going to start from down here, and I'm going to come up, and oh, the multiplicity at negative 2 is 3. That means it's going to come up. It's going to flatten out a little bit there. I could do a little bit better. Flatten out. And then head on up, because it definitely crosses because it's odd. How high does it go? Don't know. It goes up for a while. And then it's going to turn around. And let's see, the multiplicity at 5 is odd, and it's only a 1, so it crosses through in a linear fashion. And it comes down this way. I'm going to label this at negative 2 and this at 5. And I'm also going to label my y-intercept. So I'm going to substitute in 0 for x. So I have 5 minus 0 times 0 plus 2 cubed. And I have 5 times 8, or 40. So there is my sketch of the graph. Do notice that this time we didn't have 3 turning points. We only had 1, but as we know, that can happen. Let's make this our last example. We're going to sketch the graph of f of x equals 14x squared plus 5x to the 3rd minus x to the 4th. Notice our leading term is negative x to the 4th, even though it isn't written first. Remember, the leading term is your term of highest degree. So we could rewrite it, and I think I will, because I know I'm going to need to factor this. All the other problems we've been looking at have come factored already. Let's see, we have a common factor of x squared, and because my leading coefficient is negative, I'm going to factor out a negative as well. So negative x squared, and then we're left with x squared minus 5x minus 14. Now we just have that trinomial to factor. You can factor that in the normal way. So let's see, we have an x and a 7 and a 2 with the minus on the 7 and the plus on the 2. So now we're ready to analyze it the same way we did the others. Notice that the problem is a 4th degree polynomial. I already mentioned that with the leading coefficient that is negative. So I know that my graph looks something like this. Ooh, I made it look almost straight down. Let me erase then do better. In fact, it almost looked like it was curving in. That definitely is not the case. It doesn't go vertical. It just gets very steep. So our zeros are 0 with multiplicity 2. 7 with multiplicity 1, and negative 2 with multiplicity 1. So let's see how the graph will look. I'm going to put the grid over here to the right. Again, our end behavior we know will look like this. So it's going to be down here somewhere and down over here. Let's put our intercepts on. We have 0. We have negative 2. And we have 7. So here we go. Let's see. I'm going to start down here at the lower left. I know I'm going to cross negative 2 in a linear fashion because it's a multiplicity 1. Of course, it's not a line, but it kind of looks like it goes through as a line. It goes up. We don't know how far. It's going to turn around. And let's see. At 0, there's multiplicity 2. That means it's just going to touch and turn around. Whoops. And then it goes up for a while, I bet for quite a while, don't know how high, and then it will turn, and it's going to cross at 7. I'm going to label that. The y-intercept is on the origin, so I don't have any other points to label. You know, you might have an instructor who would want you to plot a few more points so your graph is a little more accurate, because notice I didn't even have a scale. Does this go up to 100 or 10,000 or 4? Who knows? We could plot a few points and figure out a little bit more accurately where it is. But in order to find this point, we'd have to use some tools that you would learn in calculus. But this is what the graph looks like. I hope you'll practice graphing some polynomial functions.